So now that we know what matter is and how to classify it, let's talk about matter a little bit more and different ways we can describe it with physical and chemical properties. First of all, let's start off with properties. Before we get into the different, which is the physical and the chemical properties, let's first talk about what a property even is. I like to tell students, think of properties as like the adjectives for your chemistry matter. I know you're trying, like, why are you bringing English into this? We're talking about chemistry. I know, but think about, what do adjectives do? They describe, right? And properties are no different. Properties describe matter, and there's physical ways of describing matter and chemical ways. A physical property is something that can be observed or measured without actually changing the composition of the substance. In other words, a physical property is a way that I can describe matter, and I don't have to actually change anything about the matter. Examples: color, density, melting point and boiling point, texture, luster, which is the same thing as a shiny. Some that might not be as clear: malleable. Malleable means that you can flatten it into thin sheets. Ductile, you can stretch it into thin wires. So for example, aluminum is malleable. Copper is ductile. These are all ways that I can describe matter, and I don't have to have a chemical reaction take place in order for that to be seen. Contrast that with a chemical property. A chemical property is the ability of a substance to combine with another substance. In other words, a chemical property is a way to describe matter or describe how the substance reacts with other substances. So, an example. If I were to say something was flammable, that is a way of describing matter. But there's no way I would have known just by looking at it that something was flammable. The only way I'm going to know that it's flammable is if I interact that matter with fire. Another example is corrosive. Okay? If I say something is corrosive, I am describing matter, but there's no way I would know something was corrosive unless it interacted with another substance. Other examples you can see here are in the chart. Examples of physical properties include the five senses. They also include the numerical descriptions I talked about, such as density, melting point, or boiling point. Chemical examples, on the other hand, are things like we talked about: flammable. Does it rust? Does it react with something? Is it acidic or corrosive? These are all ways we're describing matter. It's just a matter of, can we describe it physically or chemically? Here's an example looking at copper. So copper has a set of physical properties and chemical properties. Let's take a look at copper's physical properties. It's reddish brown, it's shiny, easily shaped into sheets and drawn into wires, malleable and ductile. It's a good conductor of heat and electricity. Its density, melting, and boiling point are given. Those are all examples of copper's physical properties, something that can be observed without actually having copper interact with something else. But an example of some chemical properties for copper are as such. Copper will form green copper carbonate when it's in contact with moist air. That's not going to happen unless it interacts with air. Copper will form new substances when combined with nitric acid and sulfuric acid. Once again, there's a chemical change. Finally, copper will form a deep blue solution when in contact with ammonia. You would have never known that unless it interacts with ammonia. So you can see the difference between the two. Now remember, those are properties. Now we get into physical and chemical changes, which, if I'm going to use my English analogy, the changes are like your verbs. So before, we were just describing matter. We weren't actually saying anything was happening. Now you have changes. A physical change is a change that happens without the chemical identity being altered. For example, cutting paper. I can cut a piece of paper and change its appearance without actually changing the substance. I still have paper. Maybe a more chemistry example would be such as a phase change. For example, let's say I had liquid water and now I have water in the gas form. You still have water, it's just the appearance has changed. So this would be an example of a physical change. Nothing new is created, it just looks different. A chemical change, on the other hand, is where you're actually changing or altering the chemical identity of a substance. You have a new substance being formed, and that's as a result of chemical changes such as rusting, corrosion, combustion, even baking is an example of a chemical change. So if I were to take a look at this picture down here, notice the substance that I have before versus the substances I have after. Notice they've changed. So this would be an example of a chemical change. To review, this chart right here has physical and chemical properties and changes. I encourage you to pause the video and reflect on this in case you have any questions about the difference between the 4 properties and changes that we've covered. With example 3, let's go ahead and look at identifying if the following are physical properties, chemical properties, physical changes, or chemical changes. So the first one, lustrous or shiny. I'm describing matter, and this is something that I can observe without actually changing the composition. So this is a physical property. Flammable is also a description of matter, so it's a property, but I can't observe that unless it reacts with something else. That's an example of a chemical property. Melting point of 15 degrees Celsius. Once again, I'm describing matter. I'm saying this matter has a melting point of 15 degrees Celsius. So it is a property, and once again, I can observe that by just simply melting something, which is a physical. So this is a physical property of matter. Baking cookies. Notice that something's actually happening now. I'm not describing matter, I'm actually doing something. I'm baking. So it is a change. What kind of change is baking? Is it physical or chemical? That's a chemical change. Anytime you bake something, there are chemical processes that happen in the ingredients that cause the formation of something new. Most of the time, it's carbon dioxide when you bake. Melting ice. Notice you're actually doing something now. You're changing something, so it is a change. But melting is just a physical change. So that's an example of a physical change. You're just changing the appearance. You still have water. Nothing new has been created. Finally, acidic. I'm describing something, so it is a property, but you would have no idea something was acidic unless you actually interacted with something else. And so that would be an example of a chemical property. There are 2 other properties I need you to be familiar with, and that's extensive and intensive properties. This is something, it's like apples and oranges compared to what we were just talking about. So chemical and physical properties are one thing, but then extensive and intensive is just a different way of looking at matter. So when we're looking at an extensive property, we're looking at a property that does depend on the amount of matter that you have. An example of extensive properties that you're probably familiar with are things like mass, or things like weight, even volume or surface area. Those are properties that it does depend on how much matter you have. For example, if I put a beaker of water versus if I put a gallon of water on top of a scale, that's going to affect the mass and weight, right? The amount of matter is going to affect how much mass or weight or volume will be there. But an intensive property is a property that does not depend on matter. One of the most common ones is density. Density is always going to be the same as long as it's the same type of matter. For example, water's density is approximately 1 gram per milliliter. What that means is 1 milliliter of water will have a mass of 1 gram. Does it matter if I have a bottle of water or a bucket of water or even a pool of water? Does water's density change? No. Water's density will always be 1 gram per milliliter regardless of the amount that there is there. And so density, along with these other ones, are examples of intensive properties. All right, so that wraps up the ways that we can describe matter. Real quickly, I want to cover the periodic table. We're not going to cover the periodic table in depth in this video, but I want to go through how the periodic table is briefly organized. If you take a look at this periodic table that's shown, you can see that the elements are colored either with this yellowish color, this purplish color, or this green color. The yellowish color represents elements that are classified as metals. And as you can see, most elements on the periodic table are metals, even the ones that are down here in these 2 rows. The green are the nonmetals, and then the purple, which there's only a few elements, represent what's called a metalloid or semi-metal, which means that they share characteristics of both. Now this periodic table does not have it, but I encourage you on your own periodic table to draw in, a staircase. And a staircase would draw right down here, just like that, okay, onward. And the staircase is what separates the metals from the nonmetals. The metals are going to be found on the left side of that staircase, whereas on the right of that staircase are going to be your nonmetals. And the metalloids, which are in purple, are lying right along the staircase, indicating that they're right in between. Also on this periodic table, it shows that which ones are solid, liquid, and gas based on if their symbols are black for solid, blue for liquid, or red for gas. That might be kind of small to see, and so I encourage you to Google another image so that you might be able to see that more clearly. But most elements on the periodic table are, one, metals, but also you can see most elements are actually solid at room conditions. So we've been talking about metals versus nonmetals. What does that mean? Well, as we've already said, most of the elements on the periodic table are metals, which means left of the staircase. Nonmetals are to the right, and metalloids are right along the stair step. And we've got the list of metalloids right here, but you can also see them along the staircase that we saw in the previous video. What constitutes a metal versus a nonmetal? Well, metals are shiny in appearance. They tend to have high melting and boiling points, because think about most metals are solid, meaning it would take high temperature to melt them or even vaporize them. Metals tend to have high densities. They tend to be relatively strong. They are going to be malleable and ductile, and they are good conductors of heat and electricity, which is why we use metals a lot of times to make wires. Nonmetals are just the exact opposite. They are dull. They have lower melting points and boiling points, low densities, not very strong. They're very brittle, and so you can't really stretch them, and they are poor conductors of heat and electricity. My recommendation is know the metals, and then just know the nonmetals are the opposite. Alright, on this slide right here, I show the groups of the periodic table. I'm hoping you're familiar with the groups of the periodic table from a previous chemistry course, but I do want to make sure I mention that you are required to know the groups of the periodic table, and that they're color coordinated based on this key right up here. Group 1, hydrogen not included. Group 1 are the alkali metals. Group 2 are the alkaline earth metals. This group in the middle here are the transition metals. Over here, starting from the right, these elements right here, group 18, are the noble gases. These ones right here in green are the halogens. And then you have your rare earth elements, or lanthanides, as well as your actinides down here at the bottom. These elements right here don't necessarily have any special names. Sometimes you might hear this group 13 as the boron group, group 14 is the carbon group, group 15 is the nitrogen group, and group 16 is the oxygen group. But they don't really have special names because they have a lot of variable properties. And so we just typically call these other metals or other nonmetals, depending on if they're to the left or the right of the staircase. Alright, in this example, we just want to get you used to looking at elements, knowing their symbols, and knowing what group they're in, as well as are they metal, metalloid, or nonmetal. So what I'd like you to do is pause the screen and see if you can fill this in to the best of your ability. Then hit play to reveal the answers. Alright, here are the answers for this. Just a few quick notes. Notice with the element symbols, the first letter is always capitalized. The second letter, if there is one, is always lowercase. Make sure that you always have the second element lowercase. Sometimes students write elements like this. For example, with manganese, they'll just make they'll make both capital, but they'll just make the second letter a little bit smaller. That would not be correct. The second letter has to be a lowercase letter. The second column is self-explanatory. In the last column with the group name, notice that we have the nitrogen group and the oxygen group because these elements don't really fall into any special type of group. If you just refer to them as, other nonmetals or metalloid, that's fine. But for the interest of being consistent, we would just give them the general names, nitrogen group and oxygen group. I did want to point out that there is a difference. Make sure that you have alkali metals for group 1 elements and alkaline earth metals for the group 2 elements. If you have that misspelled in any way, that is going to be incorrect. All right, that wraps up section 3. We'll see you in the next video.